with this more on term symbols. And I forgot that I also have this other PDF, another guide on how to go through term symbols. And I'm going to post this on the Canvas course. But this just walks you through all of those rules that I just went through. So this will be another good reference for you. And so as you scan through it, here, right, it's showing you that we can calculate it in terms of the mLs or in terms of the L values, right? It walks you through the Clebsch-Gordon series. It gives you the designations. What I wanted to do, though, is scan through to give you more of this information on those J values. Let me find that example right here. Aha, okay. So here it walks you through this example, just like what I did, where you get all of these crazy possibilities when you start including those J values. So for example, when you have a triplet D, then triplet D3, triplet D2, triplet D1 all become possible. So which of these terms corresponds to the lowest energy state? Well, we use Hund's rules to determine. And so I want to review those Hund's rules really quick, okay? So the state with the largest value of S is the most stable. So let's just talk about that for a second, okay? So S gives us multiplicity, right? And the largest value of S, for now, what we've discussed corresponds to a triplet state, right? Because S is 1 for triplet state, and 2 times 1 plus 1 is 3. So triplets are more stable than doublets, which are more stable than singlets, okay? For states with the same value of S, the state with the largest value of L is the most stable, okay? So if I go back to this list here, so all of the triplets are the most stable. So the triplet D, the triplet P, and the triplet S. Well, the one with the largest value of L is the most stable. So the triplet D will be lower in energy than the triplet P, which will be lower in energy than the triplet S. Okay? So continuing along. And so that's if they have the same value of S, right? If they have the same multiplicity. So if states have the same value of L and S, then for a subshell that is less than half filled, so we got to think about this, less than half filled, the state with the smallest J is the most stable. And I already gave you an example of that, the sodium doublet lines. Sodium is exactly half filled, right, with the 1s1. And certainly when it goes into the 3p1, it's definitely less than half filled. Well, the J1 half state for sodium was lower in energy than the J3 half states, okay? But for subshells that are more than half filled, the state with the largest value of J is the most stable, okay? So if we now kind of go back to all of these examples, you know, we don't know which ones of these are half filled or more than half filled. So we don't know. So that's once again where having the electron configuration is really useful, okay? So let's go through some of these examples. And so here that you can see how they list this, right? We note that the triplet D was the most stable, triplet P, then triplet S, and then it starts over again with the singlets, okay? And so now, so it says, since 2p subshells are less than half filled, we would predict the triplet D1 term corresponds to the most stable state. So that's because they, in this example, I lied. They actually did, they did give us that electron configuration, okay? So let's go through some of these examples for simple atoms. And I'm just going to pick out a few of these. And I would recommend that you try the rest on your own, because I'm just going to flash forward here. I've got a cheater periodic table that's got the periodic table with every single ground state term symbol. Lovely. Okay, let's go through it. So I like to go through oxygen because that's something, that's a term symbol I've actually already given you. We talked about this in Chem 361. So let's do it. So I'll remind you that it goes 2s plus 1, L, and J. And here, luckily, we have the electron configuration, so we're all doing ground state. So we note with the oxygen, I'm not worried about the 1s or the 2s because that's all going to cancel out. And then now with the 2p right here, okay, I'll kind of do my work over to the side. So here with the oxygen, my mLs, right, are -1, 0, and +1. So I have 2 electrons in this -1. So that's going to go -1, -1, +0, +1. And all of that equals -1. And the absolute value of -1 is 1. And that gives me the p term. Okay? No other possibilities. No Clebsch-Gordon necessary because I have the electron configuration. Okay. What about the multiplicity? Well, if we were to go and add up all of the spin states for this thing, we would in fact see that we have 4 electrons to consider, right? But these 2 electrons, they're paired up, and they're going to give me an s equal to 0. So that pair is going to cancel out. So what I have going on right here, I have 2 unpaired electrons, and those 2 unpaired electrons definitely correspond to a triplet state. Okay? And so I'm just checking my notes to make sure. Yes. So, because right, that would go 1/2, -1/2, which would cancel, and then +1/2 and +1/2 to give me 1. 2 times 1 plus 1 is 3. Triplet. The other thing to recognize is when we see 2 unpaired electrons like that, even though we have a paired state, the paired state is going to cancel out. So you could really just look at this and see 2 unpaired electrons. Automatically, that's got to be a triplet. Okay. Now, what's the appropriate J value? Well, we know that J, let's back up and look at that for a second. J is L plus S all the way down to L minus S. All right? So if S is 1 and L is 1, we could have triplet P2, we could have triplet P, or triplet P1. I think that I made a mistake on this. So when S is 1, oh yeah, 1 and 1 is 0. Okay, good. So yes, all of these become possibilities. Triplet P2, triplet P1, triplet P0. So which one is it? Well, if the state, let's see here. Okay, for subshells that are more than half filled, state with the largest value of J is the most stable. So that means my ground state here on oxygen would be triplet P2. But oftentimes we see an oxygen atom just listed as O triplet P. Hopefully maybe you remember that from our kinetics. Because that J equals 2, that non-half integer state is less important for the spectroscopy. So we would list that as O triplet P. Okay. So let's do another one here. Let's see, do I have sodium on this list? No, I don't, but let's put it on this list anyways. Na, and so we know that it looks like this. So I want to put sodium on this list because I started this discussion talking about sodium. Okay, we know sodium is all filled up and it's 2s, and then finally sodium has a 3s1. So it's given as helium, or rather neon, so that's given as neon 3s1. So we can ignore all of those core electrons, and there's only one single electron to deal with, a 3s1. Okay? And so because that's a 3s1 here, oh yeah, so excuse me, this is the ground state of sodium we're doing. Yep, okay, good. I confused myself once again. I told you this is like electron configuration on crack. So 3s1 corresponds to an L equal to 0, which gives me an S. It's a doublet, right? That's the only thing that I have to worry about. It's only one electron. And so if I recognize one electron system as a doublet, I can automatically put a 2 right there. But for all doublets, J equals 1/2. So now this is going to be, the only possibility becomes doublet S 1/2 because 0 plus 1/2 is 1/2. I can't go to the negative 1/2. So doublet S 1/2 is my term for sodium. And if we go back for a second here, yep, there it is. The ground state, doublet S 1/2. So then how did we get the doublet P 3/2 and the doublet P 1/2? Well, remember, that corresponds to the 3P1, okay? So because it's a 3P1, now my L is equal to 1, which gives me the capital P. It's still a doublet, but now because it's a doublet and a P, and remember, J takes on all values L plus S all the way down to L minus 1S, minus S. That's where then we get the doublet P 3/2 as possible and the doublet P 1/2 as possible. Okay? So moving on, more examples. So let's look at this neon configuration. Okay? Let's do neon. And so once again, neon is all populated up, okay? So we would have 0 plus 0 plus 0 plus 0, right? Zeros all the way through. And if you don't believe me, right, we know that this is 0 and this is 0, but if we look at how all of these terms add up, right, it's going to go -1, plus 0, plus 0, plus 1, and that all equals 0, okay? So we would start for neon. Here, I'm going to make sure that we note that that's for oxygen, and this one was for sodium. And then for neon, we're going to have a capital S because all those mLs added up to 0. We note that because they're all paired up, automatically we can note that that's a singlet state. It has to be a singlet state. They're all paired up, okay? And then now and because it's a singlet state, remember up here, for 2s plus 1 to equal 1, that means S has to be 0. And for my J term, it's L plus S, and so the only possibility is 0. And here we arrive at a very special term symbol. All closed shell species are 1s0. So for example, if I was looking at sodium plus, we recognize that sodium plus has the same electron configuration as neon. So of course, sodium plus would be a singlet S0 term. And so that's really important for us to recognize, okay? I want you to recognize that all closed shell. And so first of all, recognize what all closed shell means. It means it's isoelectronic with a noble gas. So closed shell means it has noble gas configuration, right? So all 1s0 terms are closed shell term symbols, okay? So let's do an excited state here. So I'm going to go to a new page really quick. So let's suppose we have excited state oxygen. So just to show you where we're going with this, so we recognize that ground state oxygen was 2s and 2p, so it looked like this, and that main term was a triplet P. Technically, it's a triplet P2, but we mostly just notate it as a triplet P. So how do I make an excited state out of this thing? Well, this is where we're going to have fun breaking all of those electron configuration rules. So one way I can make an excited state, and as it turns out, it's the first excited state of oxygen, is by forcing this triplet to adopt a pair. So, right, I've moved that over, I've forced it to pair up. So we can see that as far as what the letter is, so that's going to be -1, plus 0 to be -2. The absolute value of -2 is 2. So that's a main D term. Okay. We can see that these are all paired up. It's all singlet. So that's a singlet D. And then technically this would be a singlet D2. Okay. So that's how we deal with excited states. We're going to start like literally breaking the rules and moving electrons around to where we know they shouldn't go. So now backing up here, so here is my cheater periodic table. And there's some really cool stuff we note here. So for one, check out the noble gases, right? Look, they're all singlet S0 because they're all closed shell. Oops, and I circled that and I wrote over the next thing I wanted to point out. Check out all of the halogens. The halogens are all doublets, right? There's fluorine, it's a doublet. It's got one unpaired electron, okay? And because it's a doublet, they're all going to have either that 3/2 or 1/2 state, but because these halogens are more than half filled, it's the large value of J that's the most stable. And look, as you scan down the periodic table, they all have the same term symbol, which is awesome. And then look, there's that triplet P2 for oxygen. Sulfur has the same term symbol, and so on. Okay. And then now, what's really cool when you look at boron, if we go back to boron here, boron is a doublet, right? But it's less than half filled. So whereas fluorine is doublet P 3/2, boron is going to be doublet P 1/2 because it's less than half filled. Okay, and then similarly, when you look at carbon, carbon is also a triplet state, just like oxygen, but because it's less than half filled, it's the triplet P0 that's more stable, whereas oxygen, it's the triplet P2 that's more stable. If we look over to here at our group 1, we can see they're all doublet S1/2, which is really cool. And then now look at this, beryllium, magnesium, calcium, they're all closed shell. They closed out the S shell. Or subshell, I should really say. But all the same, they're all closed shell, so we get that singlet S0. And now there's a couple really interesting examples as we start to look at the periodic table. So let's look at this, what series did I want to look at? Yes, let's look at the iron series, okay? And so this gets complicated into the transition metals, right? It's a pentuplet. So it's 5, right? So if 2s plus 1 equals 5, S had to be equal to 2. So where did we get S equal to 2 from? Well, look, plus 1/2, plus 1/2, plus 1/2. Oh, wait, I can't do math, can I? No, I can do math. 1, 2, 3, 4, 5, plus 1/2. I was confusing myself because of the way I drew that arrow. Let's get rid of that arrow. Okay, plus 1/2. So for iron, it should be 1, 2, 3, 4, 5. It should be S equals 2/2. But why is it equal to 2? Well, because the observed electron configuration for iron is not 3d5, it's 3d4. Okay, 1, 2, 3, 4, 5, right? Remember that. I'm confusing myself. It's not 3d6, it's 3d4. Okay, apologies. But all the same, as you scan down the series, you can see that now, here's where we're starting to see exceptions to the electron configuration, right? And you can even see that there's a lot of questions next to some of these because it's not clear what's the lowest ground state. Okay, so this is pretty intense going through this term symbol stuff. As I said earlier, it's like electron configuration on crack. And even I confuse myself with all of the exceptions and so on. So the main thing is that you can do the common elements, work through these examples that I gave you and compare them to that periodic table. And what we're also going to do next is what I also want you to do is review this document that I'm going to post, particularly with how we can line up what's most stable and what's least stable. And then finally, I'm just going to talk about this very briefly. We can talk about all of these selection rules using term symbols. And I'm not going to spend as much time lecturing on this because here I've got it in this document. But here are our term symbols given by the same rules we had before, right? But now we can recognize these term symbols, or excuse me, we can recognize these selection rules from their term symbols, okay? And so this notation right here, but J, so what this means is cannot go from J equals 0 to J equals 0, but that's only for very light atoms, for the less massive atoms. And what we're also going to start to see as we go down the rabbit hole even further, there are times in which these selection rules can absolutely not be broken. But of course, because chemistry is the science of exceptions, there are also definitely times when these rules can be broken. So that's why I'm not going to spend as much time with this, because again, this gets into the crazy, like all of those rules like you learned in inorganic chemistry for the exceptions. I don't want to spend as much time with the exceptions. I really just want to kind of spend time going through the main observations. Okay, so this here is the helium spectrum. So this is for helium. And of course, everything down here is 1s0, ground state helium. And so you can see that helium, if you recall, we started this discussion noting that with helium 1s2, when we go to promote it to its first excited state, that's a 1s1, 2s1, which can create a series of triplets or a series of singlets. And here we can see that. So here is our series of triplet states, and here is our series of singlet states. And so you can see that the L value can be 0 or plus or minus 1, but not plus or minus 2. So I can't go from a D term to an S term, but I can go from a D term to a P term, or an S term to a P term, or I can also go from a, let's see here, here we're not seeing any P to S, or excuse me, P to P. No, there is one right there. I just missed it. There is a P to P term right there. Okay. But what's important to note it is there's no singlet to triplet conversions. That's forbidden. And so that's given by, where is it? Right here. Delta S has to be 0. So that is a forbidden transition to go from a triplet to a singlet. And that is never, hardly ever observed in atoms, but oftentimes in molecules, we can get conversions from singlets to triplets. And I'm going to talk about more of that exception with molecules as opposed to atoms, because very rarely do atoms, especially the lighter atoms, very rarely do they break these rules. Okay. So let's see. I'm just going to see if there's anything else to go through. So this is a really handy guide to go through. I think they also show us here. Yes, so they kind of described what I was going through. Perihelium, as it turns out, because it's you get different magnetic states of helium because of the electron configuration. So perihelium corresponds to the singlet, orthohelium corresponds to the triplet. Let's see what else we have here. I think, yes. So this is giving us a diagram for hydrogen. Okay, and so this is now all the levels. It's showing you the splitting of all the levels for hydrogen based on the fact that hydrogen is a doublet state, right? A one electron system. So there's going to be tons of splitting for hydrogen being a doublet state. And all of these arrows give you the allowed rules, okay? So fantastic. So I went through that kind of quick, but you know, like doublet, triplet, spinlets, be familiar with spin orbit coupling. We went through that. And then I want you to spend a lot of time on practicing these term symbols on your own, okay? For the simple atoms, for the common things. Okay, folks, that's it for chapter 9.